In this lecture, we're going to review some basic relationships between stress and strain. So I'm going to review what many of you have already studied in basic strength of materials course. If you're taking, for example, the advanced strength of materials course here at UCLA, then you'll be very familiar with the terminology. If you haven't, then this will be a good opportunity to kind of brush up on the definitions of stress and strain and the relationship between stress and strain. So before we start, I wanted to point out that most failures occur as a result of excessive deformation. One way or the other, plasticity plays an important role. So unless it is otherwise specified and carefully considered and planned, as in your project, then plastic deformation will be considered as a manifestation of damage and failure. In some cases, around fillets and corners, you can allow plasticity to relieve the stress, which is part of the planning, but the designer has to be aware of such situation. Otherwise, we will just look at crystals as material, part of the material that will deform, and the deformation is usually leads to concentration of the deformation mode, the plastic deformation mode, in a small volume of the material, and leads to failure by an instability type of situation, like a necking instability, which we'll consider in the next lecture. However, we can, for just simplicity and for initiation of our analysis, we can consider the deformation as homogeneous, that if we take a bar and apply a force on that bar, then we will average the plastic deformation over the entire volume of the bar. If it is an elastic range, then we don't have to worry about it, because elastic deformation is by necessity uniform and homogeneous all over the crystal. Only plastic deformation that we need to worry about, whether it's localized or uniform. So I'm going to just remind you of some of the earlier analysis that you've taken in relationships between forces, areas, stress, and strain. So let's take our standard bar in here, and the standard bar is under the application of an axial force. Then if the initial cross-sectional area is A0 and the initial length is L0, then we're going to define the engineering stress as the ratio of the force divided by the initial area, the engineering strain as a change in length divided by the original length, and this will be L final minus L0 divided by L0. So this will be the definition of the engineering strain in this case. Next, if we have the pulling the bar, it will go through the elastic range of deformation first, which is right here, and then it will undergo yielding. So if this is the stress and this is the strain, then you will have a yield, which means that you get a lot of deformation for very little increase in the applied stress, and then you get hardening, which is this range here. This is hardening because you need to increase the stress to continue increasing the strain. And then finally you get rupture when the strain exceeds a critical value epsilon sub f, which is a failure type strain or a rupture strain at the end of the experiment. First, we wanted to note that the area under the curve here in the elastic range is considered to be, we know that the work done is the integral of sigma d epsilon. This is the work done per unit volume from our strength of materials course. And sigma is a tensor, and epsilon is a tensor. So this means it's a summation over all of the different components of the stress and the corresponding components of the strain. Here we have only one component of stress, one component of strain, and therefore we can determine the work done as the area under the stress versus strain curve, which happens to be kind of an easy process because it is linear, the relationship is linear, and therefore we have to just calculate the area of the triangle, which is half times the width times the height, and the height is S yield, the yield strength of the material, and the relationship between the stress and the strain is that sigma is equal to E times epsilon in the elastic range, and from that we get this quantity. The quantity that we get is called the modulus of resilience, because it's just an indication of how much energy can be absorbed in the per unit volume in the elastic range, and it is the yield strength squared divided by 2 times the elastic or Young's modulus. If we consider now the entire deformation process, and we want to know let's say in a car crash, it is important to absorb as much energy as possible all the way to plastic deformation. We're not worried about fracture or anything of that nature. We just want to absorb as much energy as possible. Then we must now take the area under the curve for the entire curve, both in the elastic range and in the plastic range. This area under the curve is the integration of sigma times d epsilon, and the integration is from the beginning of the experiment, where the strain was 0, to the end of the experiment, where the strain was the rupture strain. And therefore we're going to call this integrated amount of work as T, and T is the modulus of toughness of the material. So if you are designing materials that have to withstand crash applications, then you would select materials with the highest modulus of toughness possible. Continuing on, we want to now relate the stress and strain of engineering with the engineering definitions that we had before. Engineering are based on what we call the reference state. So the reference state is the initial configuration. A0 is the area and L0 is the length. That's our basis. That's for engineering stress strain. However, if we have significant plastic deformation, then the material is going to extend, and L0 becomes L, and the area will shrink from A0 to A. So A0 becomes A, and L0 becomes L. A0 is decreasing, and A0 decreases to A, and L0 increases to L. So we would characterize the material now. The stress state can be measured in the deformed state. And when we measure it in the deformed state, we're going to call that the true stress and true strain. So having said that, then the true stress will be equal to the applied force divided by the current area, and not the reference area. So the current area A, and we're going to call sigma now sigma prime, just to differentiate it from sigma. So it's a symbolic differentiation, not a differential, but we want to contrast it to sigma. So if we use sigma, it is engineering. If we use sigma prime, we mean in the deformed configuration. The true strain, however, is obtained by an incremental process by which we add up the strains in a in a step by step as we stretch the bar. Adding up means integration. So you're integrating dl over L, that's the incremental strain. So you're integrating dl over L from L0 to LF, from the initial to the final. When you do this integration, you get natural log of L final divided by L initial. And that is called the true strain, and we're going to give it the symbol delta. So if we now want to make a relationship between the engineering strain and the true strain, all what we have to do is write delta L as L final minus L initial and make this division. So we have L final over L0 minus 1, and we know now L final over L0 is e to the delta. So we have now epsilon is equal to e to the power delta minus 1. And we can reverse this relationship and write it as delta is equal to ln 1 plus epsilon. So in our minds, this makes sense, because if epsilon is very small, then delta will be approximately equal to epsilon. If epsilon is large, then delta will be larger than epsilon, because you have ln of 1 plus x is greater than x in general. So with that, we have a way to treat the relationship between the true strain and the engineering strain. Now, if you want to make a relationship between the stress and the strain, then I have to find the stress measured in the current configuration, in the configuration where I have actually an area that is reduced in extent. So in order for me to find this relationship, I need kind of a connection between the reference state and the current state. And the connection that we'll use is that in a plastic deformation, if it is the most prevalent mode is plastic, or the majority of deformation is plastic, then there's no volume that will be increased or decreased. So it's called a volume conservative deformation. And if the deformation is volume conservative, then approximately the product of the area times the length will be the same in the reference and in the current configuration. And therefore, the ratio of L over L0, that is in the value of the engineering strain, which is 1 plus epsilon, this ratio will be the reverse of that if it is written in terms of area. So it will be A0 over A. Why is that important? Because when I write the true stress sigma prime, it is P over the current area, and I can substitute the current area is equal to the original area times the original area over the current area, A0 over A. And A0 over A turned out to be that it is equal to 1 plus epsilon. So all of a sudden we have the current stress is equal to the reference stress, but it has another factor of deformation coming in, which is 1 plus epsilon, and 1 plus epsilon can also be written in terms of delta, because we know that 1 plus epsilon is e to the power delta. So you can write it either this way, or you can write it e to the power delta and times sigma. So you have now a relationship between the stress in the current configuration and the stress in the engineering configuration, or the reference configuration, and we can go back and forth between these two relationships. Now let's just review what we mean by stress. And the stress is defined as a force intensity. So the force intensity is now something that we will need to highlight, because it is, the intensity means the force per unit area, and it is on a given plane passing through the point in the body. So in order for us to get this force intensity, we need the direction and the magnitude of the force, and we need the plane on which the force acts. So we need two different types of information to write what the stress is. And therefore, we can see that the stress is requires a knowledge of the plane and knowledge of the direction. For example, if I cut a cube inside the material, and this cube I have a force that goes into the x, if this is the x direction, is there in this orientation. This is x, for example, or maybe I should just make it consistent. I'll make this x, and I make this y, and I make this z. So I have the right-hand rule. Then if I have a force going into the y direction, then the direction of the force is y, but also there is a normal component to this plane, and the normal component is going into the y direction. So the normal component is in the y direction, and the force is in the y direction. This is the force, and this one here is the normal component of the that is in the y direction. So both vectors n and f are going in the same direction, and both directions are in the y direction. Therefore, if I write the stress in here, it will be sigma y, where the first y is the direction of the force, and the second y is the direction of the normal vector to the plane. Having said that, I can say that if I have now on the same face, and I have a force going into the x direction, then the stress associated with that will be sigma in the x direction, but the normal to the plane is still in the y direction. So that will be sigma xy. And finally, if I have a stress in this direction, I can write it as sigma, and sigma now is in the z direction, and again the normal is still in the y direction. So you need two indices to indicate the total stress in this case. And for simplicity, instead of using sigma xx, a lot of times we use sigma, we take one subscript as a summary of the two, and to indicate shear, instead of using sigma xy, sometimes we use tau xy. Another notation is the index notation. If we take I is in the x direction, if we take j to indicate the y direction, and if we take k to indicate the z direction, then instead of using x, y, z, then we can use I, j, k as indications of the axes that we are concerned with. So in this case, if I write sigma ij, it means that this is the stress that is in the I direction, force is in the I direction, and the normal is in the j direction. In the previous example, I, if it is in the x direction, then we can say I is equal to 1. And j, if it is in the y direction, we can say j equals 2. And k is in the z direction. If we specify the direction, then it would be k equals 3. So for example, if I say sigma 1, 2, I mean that this is sigma x, y, because when I is equal to 1, then it means in the x direction, and when j is equal to 2, it means it's in the y direction, and so forth. So all of that are symbols that we're used to. So again, we emphasize here the stress state on each face. You have always 3 components of the stress, and you have one is a normal component and 2 are shear components. And we want to note that as a result of the torque equilibrium inside the material, then tau, for example, xy is the same as tau yx. This is a result of equilibrium of torques, and therefore we just doesn't matter whether we use xy or yx in standard elasticity situations. The strain is also what we call a tensor, and a tensor is like a matrix. It's a 3x3 matrix, but it is a symmetric matrix. Therefore, 3 components are equal to the off-diagonal components, and therefore we have the strain can be represented like this, epsilon ij. You have it represented as a matrix, and the matrix is epsilon 1, 1, epsilon 1, 2, epsilon 1, 3, epsilon 2, 2, epsilon 2, epsilon 2, 1, epsilon 2, 2, epsilon 2, 3, and then epsilon 3, 1, epsilon 3, 2, epsilon 3, 3. So a matrix like that is equivalent, similar to what we've done for the stress. For example, if you write epsilon xx equals to to what it is, it is du by dx, and u is a displacement in the x direction. So this displacement in x direction. And you just measure displacement in x, and you divide it by delta x, and that gives you the strain in the x direction. It's like increase in length divided by the original length idea. And the shear strains are given by this type of relationship, where you have gamma is used instead of epsilon. Instead of epsilon xy, we use gamma xy, which is now equals to twice of epsilon xy by convention, is the sum of 2 components. One is du by dy, and the other one is dv by dx, and each one measures the angle, deviation angle, from the corresponding axis, either x or y. So when it is symmetric, then the 2 angles add up to a factor of 2 in here. Going a little bit fast because this is already in your strength of materials course. Finally, if we have stress and strain in 3D, then the relationship between the stress strain is that we always write it in Hooke's form. The epsilon x, for example, is sigma x over E, as we know, but we subtract the Poisson contraction as a result of application of stress in the y and the z direction, and then we add the thermal strain on top of the mechanical strain to give us the total strain. So this type of relationship are for normal stresses and strains, and then this is combined with 3 other relationships for shear stresses and shear strains as well. And the relationship, there are some relationships between the Young's modulus and the shear modulus that you may be familiar with. And the shear modulus G is a little bit less even than half of the Young's modulus. It's E over 2, and then you have 1 plus nu, Poisson's ratio. These are all relationships that we need to kind of refresh our memories. So we have gone through that, and we now finally can write the stress as a matrix, and the matrix is of this form. It's a 3x3 matrix, but the off-diagonal components are symmetric. So these components are symmetric with these 3 components. And we can use this index form, or we can use the Cartesian form. So either index or Cartesian. So Cartesian is right here on the right, index is on the left hand side. If we take the diagonal components and add them up together, sigma 1 1 and 2 2 and 3 3, we get a summation convention. Sigma I will be the sum of these three, and since we sum over I and I, we call this a dummy index. It's the same as summing over J. So you're summing over J or K, it doesn't matter. It's the same as summing the diagonal elements of that matrix. An application of the summation convention as an application, if we're calculating, for example, the work done per unit volume, then we write it as sigma ij d epsilon ij. Whenever we have repeated index, it means it's a for loop, like you're doing a for loop for I equals 1, 2, and 3. And then you have another for loop over j, so you have for j equals 1, for j equals 1, 2, and 3. So you have two nested for loops to evaluate this result that you see on the board, and that is actually the work done per unit volume in 3D. One final note is that the symmetric tensors, symmetric means that it's a matrix, therefore the off-diagonal terms must be equal. So Aij is the same as Aji. We call this a symmetric tensor. If the off-diagonal terms are equal but opposite in sign, we call this Q-symmetric. So we can differentiate with the it's like a matrix, but the top half is negative of the bottom half off the diagonal, and that gives us a skew-symmetric tensor. And if we have a skew-symmetric tensor, obviously we would expect that the diagonal terms are all equal to 0 for that case. And then finally here we realize that we have any tensor. We can show that any tensor Aij can be split into two components. One is a symmetric tensor Eij, and another one is a skew-symmetric tensor Pij, and that is easily done by looking at the writing the tensor like this. If we just write Aij as equal to 1/2 of Aij plus Aji plus another 1/2 of Aij minus Aji. So if we write it like this, this term here is obviously a symmetric tensor, and this term is the same as Pij, which is a skew-symmetric tensor in nature. And with that, we have finished a quick review of stress-strain relationships in 3D, and we're ready to move on to the next lecture in the course.